Yeah, okay, we'll get going. So I've done this pretty much the same version of this presentation before. So what we're going to do is it's mainly aimed at people who are new to this and are not familiar with the different kinds of telescopes particularly and the accessories that you use with them. It can be pretty confusing. So I'm going to start just by talking about a couple of principles that all telescopes use, and it's to do with optics. We won't delve into it too much because it can quickly become a really complicated subject, but we will just take a look at the this image here. It's a little bit misleading, but if I can, and I'll explain why it's misleading a bit later. So you've got a ray of light coming down here. This is just a circle showing you angles. The ray of light hits a surface and you can see that it gets deflected. And then there's a fainter ray that goes off that way. So what this is illustrating is a principle called refraction. So you've probably seen this yourself with water. If you do if the water is smooth, you get reflection, or a bit of a fainter reflection off the surface. Most of the light goes through, but it gets deflected. And if you put a ruler, say, in a glass of water, you'll see it looks like the ruler is being bent, and that's caused by this phenomena. Now, it turns out the ancient Greeks knew a little bit about this, and right through to the Middle Ages, and they had what they would call burning glasses, where they were used to concentrate the light of the sun, sometimes using a natural glass, and they could shape it to not just do this, but use that or refraction effect to focus the light. So we'll just go on to the next slide. Incidentally, this is what is used for a refracting telescope. It was invented over 400 years ago now. Does anyone know who invented it? Newton. No.
Cassegrain.
Yeah, sorry? Yeah, it was. Well, we don't actually know for sure who it was. It's a guy, a Dutch spectacle maker named Hans Lippershey is credited with inventing it, but he tried to patent it, and the patent was rejected because it was disputed by other spectacle makers who all claimed that they'd actually thought about it first. And so shortly after that, once it had been demonstrated, basically the news of it spread like wildfire, and in Italy, Galileo learned about it and made his own, which was an improved version. And of course, he was the first to turn it on the skies, and as we know, he made some really amazing discoveries, such as the planet Venus had phases, just like the moon. If you have a telescope, we have a chance to look at Venus in a telescope. It's quite amazing to see it because it's unexpected. You see Venus with the eye just as a really bright star, but when you look at it in a telescope, it actually can be in a crescent phase or a quarter phase or a gibbous phase, just like the moon. And Galileo realised that this was evidence for the heliocentric theory, that he could explain those phases of Venus if it was orbiting the sun. So it was quite an important discovery. So we'll go on to the next bit. Yeah, that's right. Yeah, you don't get it with Mars does and Jupiter do have very slight phase effect, but it's only a slight darkening on one limb or the other. It's because the sun is always shining on them from the point of view of the Earth. But we can, in the case of Mars especially, you can see a little bit round the corner, so you'll get a bit of limb darkening on Mars. Okay, so don't worry too much about these equations here, but the previous diagram, this is what scientists in the past came up with. In fact, it goes back to, I think, a Persian scholar back in the 10th century was interested in these burning glasses, as they called them, and he was trying to optimise how you would shape the glass to get the best effect, like for starting fires, that kind of thing. And this is a more general solution than he came up with, but he basically got the idea of how you could optimise the shape of a simple lens to focus light. And so this is called Snells Law, and the reason refraction works is that you've got up at P, there's usually air, and then you have an interface, and then usually glass, but it can be any two substances that are transparent, and you've got these numbers, which is V1 and V2, and that's actually the speed of light in that medium. So when light is passing through air, it actually travels just a fraction slower than in the vacuum, but it's very close because the refractive index, as it's called, of air is something like 1.00002, something like that, or 3. So the speed of light when it comes from outer space, comes into the air, it doesn't change very much, so there's very little refraction, except you see stars twinkling, and that's because different temperatures, layers in the air have a slight different refractive index. So basically the sign of the angle of incidence to the angle of refraction depends on the speed of the light in the two media. And the way that's characterised is by this number n, which is called the refractive index. So outer space, the refractive index is 1. So light travels at the speed of light here. It's just slightly over 1. So the light is slightly slower than the speed of light in vacuum. But when it gets to glass and different kinds of glass, the speed will be different. But there's a little trick here which caused a problem for Galileo, is that this equation, the actual value of the refractive index, is different for each colour of light. So that's a bit of a problem, and we'll see why. So this is a phenomenon called dispersion, and this is why the first refraction ray going through a surface, a bit of reflection, a bit of light being refracted, was a bit misleading, because in reality the beam of light was white, so it's a mixture of colours. What really happens is that the beams of light get dispersed like that because the refractive index is different for each colour. So Sir Isaac Newton actually used this effect to measure the properties of light, and he discovered he could recombine all these different colours and get white light back again. So he did a lot of experiments with prisms, and one of the books he wrote called Optics. So that basically set the foundation of I guess, modern physics, optical theory. He was wrong about quite a few things, but that was the start of it. And this is just chart is just showing that there's a whole lot of different kinds of glass that are used in lenses and cameras and telescopes and eyepieces. And this is showing you the wavelength along the bottom and then the refractive index on the top. And you see each glass has quite a different curve of the refractive index. So a clever guy... Oh, actually, I've got this out of... I'll come back to that. Eventually figured out a way that you could use this dispersion to fix the problem. So this is a normal lens, such as the sort Galileo used. His was actually simpler, where it was only curved on one side and flat on the other, but you get the same effect. The curvature of the lens brings the light to a focus. But the problem is the different colours focus at a slightly different position. And so if you look at a star, you'll see there'll be a sort of rainbow effect around it. And that's called a chromatic aberration, which is a bad thing for optics. So we can get around this partly by making the curvature less, so the focal length is a long, long way out, and then the amount of error isn't so bad. But you get a pretty unwieldy telescope like this one. So I think this was Helvenius came up with this idea that he would have an objective lens right up the top there, and you can see the eyepiece down the bottom, and it's pretty impractical to use. But there were quite a number of telescopes back in the 18th century where they tried this with very limited results, as you can imagine.
What's that on the top of it, do you think?
Sorry? Yeah, there's somebody up there that's obviously hauling on the pulley to make adjustments. I wouldn't want that job, I think. A bit tougher than being an astronomer these days. Okay, so if you're buying a refractor nowadays, the cheaper ones actually always have at least 2 lenses in the objective. And this is an example of there's various combinations, but the idea of it is you combine 2 different kinds of glass, and you can make use of the fact that their refractive indexes are different, and by cunning design you can bring 2 colours to the same focus. Fortunately, you can't get all of them to the same focus, so if you buy a standard refractor, usually a visual one, you'll see on really bright things there'll be a purple fringing of the out of focus purple end of the spectrum is where they normally design visual refractors. So this couple of people invented this idea independently at Chester Moore Hall and John Bolland, and so that was way back in the 18th century. But nowadays we have access to more sophisticated optical materials, and you can buy these. They tend to be quite expensive. Has anyone got one called an APO refractor? Or you might see camera lenses also marketed as being APOs, which means that they have pretty much 0 longitudinal chromatic aberration, and they achieve that by combining some fairly unusual kinds of glass with the more standard optical glass. So an example, sometimes they use a marketing term of ED, extra low dispersion, and one of those types of glasses is mentioned there. O'Hara's a Japanese company, not Irish, and one of the optical or the ED glasses is called FPL 53. And some manufacturers use calcium fluoride, which also has suitable characteristics for making APO lenses, but the problem is it's a very soft material, so you'd never use it as the front element in the lens. You would normally have it behind the front element, which would be a more robust type of glass. Okay, now I'm going to, what happened there? Somehow there we go. I'm just going to go back because I had this slide out of order. So that's refractors. The other principle I wanted to talk about was reflection, and you can see here, similar to the first picture, we've got a ray of light coming in, bouncing off a mirror, and the trick about this is the angle of incidence is always equal to the angle of reflection, and you notice that there's no, and this is realistic because you don't get any chromatic errors with a mirror. So all wavelengths get reflected exactly the same way until you get up to things like X-rays or where they start to actually penetrate the surface. So what you do get, and not shown here, is there will always be a little bit of scatter. So that depends on how good the optical surface is. If it's really smooth mirror and it's really good, usually they use aluminium these days for the reflective coating. If that's been well applied, then you shouldn't have too much scatter. So we can obviously if we have a curved mirror, we can actually use it to focus light just like a lens. And Sir Isaac Newton thought of this. And if I bring it back, find the right slide. So Newton built the first reflecting telescope, and it's a lot easier to design than a refractor, because you have one surface of the main mirror at the back to figure into a curve, rather than having to worry about two sides of the lens or four sides with an achromat. So those are more difficult to manufacture. And you have a flat secondary mirror, which is relatively easy to polish flat. And you see the light is reflected by the secondary out to the side through a focuser, and thus it's still a really popular design today. If you hire most of the telescopes the Society hire a Newtonian design. And the common ones are on a really simple rocker box mount that was popularised by John Dobson, so they're called Dobsonian telescopes. So it's really a Newtonian sitting on I guess you call it a Dobsonian mount. So the original Newtonian reflectors had a spherical mirror, and it turns out that if you have a short focal length on a mirror like that, then the rays hitting different parts of the mirror don't come to focus at the same point. It's an optical error called spherical aberration. So you can fix this if you figure the surface of the mirror to be a parabola shape. That still has another error called coma, but I won't worry about that too much. The parabola means that you've got really excellent on-axis quality of the image. And so, if you buy a reflector, a Newtonian reflector, you want to make sure that it's got a parabolic mirror, either that or it's got a really long focal length, where the difference between a sphere and a parabola becomes pretty negligible. So, but if it's a f5, f6, you definitely want a parabola. If you don't know what that means, the F ratio, or the F number, is the ratio of the width or the diameter of the mirror to the focal length. So if you've got a focal length of 6 metres and you had a 1 metre wide mirror, that would be an F6 telescope. Okay, Newtonians, you think, oh, okay, they're really simple, so they're okay for beginners and that, but maybe they're not so good. But in fact, if you came to Rolf Olsen's talk last week, he uses a Newtonian reflector for his images, but he uses a special corrector called a coma corrector that makes the image sharp in the corners as well as in the centre of the frame. So yeah, definitely don't write off the Newtonian if you want to get into imaging. Just needs a bit of extra work done on it. Okay. So here's another kind of reflector, and this was invented by a gentleman named Cassegrain. And if you've seen the Zeiss Telescope upstairs, it's exactly this design. What happens here is that, whoops, not that. Okay, that's a bit better. So you have a parabolic mirror, main mirror, and this time, instead of having a flat secondary to deflect the light out of the side of the tube, you actually notice it has a convex lens, so it acts as a magnifier in effect, so it's increasing the effective focal length, and so it reflects the light and focuses it behind the main mirror. So for that to work, you have to have a hole in the main mirror, and that's how the Cassegrain works. The Zeiss upstairs has got a 0.5 metre diameter primary, and its effective low focal length is 6.6 metres, so quite good as a telephoto lens with a camera on it. Okay. And we've got lots of variations of the Cassegrain idea. This one is a Ritchie Creation telescope, which is a design used by most of the large observatories. There are some more exotic ones again. This one looks pretty complicated, but instead of being in a simple tube, it's the different parts of the telescope are supported by truss poles, and that's done mainly to save weight rather than having a huge solid tube that would be really heavy. And so the truss poles can be really strong and rigid, but saves a lot of weight in your telescope. Especially a lot of them nowadays are made out of carbon fibre. So the Zeiss is a truss pole telescope, but it's made of steel, so it's still quite heavy. Whereas a lot of them nowadays, you get them made out of carbon fibre poles, which means that the actual structure of the telescope is quite light. The main difference for this telescope is that the secondary and primary mirror are both shaped as a hyperbola, and this is actually quite difficult to fabricate and get it right. The Hubble Space Telescope used this design. When it arrived in orbit, they found that the main mirror had been figured wrong, and so all the images that came down had a suffering from astigmatism, just like you get the human eye. If your lens in your eye is having problems, you can suffer with astigmatism. You get corrective lenses, eyeglasses to fix it, and they had to do the same thing with the Hubble Space Telescope. So they had a special space shuttle mission to install corrective optics, because somebody had basically done the wrong test on the main mirror before the telescope was launched. And the really strange thing is that the spare mirror was actually correct. Problem was it was still on the Earth. And there wasn't any real way to swap out the main mirror in space, so they had to do some fixes. The other features you can see here, you see that black tube, and there's a larger tube around the secondary mirror here. What they are, therefore, is to block out any stray light coming from where you don't want it. So, especially with this kind of telescope where it's obviously completely open, so if you had ambient light coming through here bouncing around, it could get down into your eyepiece or camera and mess up the contrast of the image. So these tubes are just there to act as baffles to block out any stray light. And you can also, you see some of these type of telescopes, they will wrap a black shroud around them as well, which also helps either absorb or block out any stray light getting into the system.
My refractor has got that's my 80mm triplet, or what you said before. It's also carbon fibre.
Okay, yeah.
That's,
so the tube, having a carbon fibre tube even will save weight.
Yeah.
They tend to be more expensive though.
Yeah.
So that's the downside over a metal tube. Okay, we've got another kind of telescope which is basically a hybrid of the two sorts we've talked about, where we had the refracting telescopes, which were just using glass elements to focus the light, and the reflectors that have mirrors to focus the light. And this type of telescope sounds quite complicated, but they use a combination of reflection and refraction. And the most common one that amateurs will be familiar with is called a Schmitt Casagrain. And there's also a thing called a Maksutov telescope. So we'll have a quick look at those. So this is a Schmitt Casagrain. It's still the same basic Cassegrain idea. We have a primary and a secondary mirror that focuses the light through a hole in the primary mirror. But this one, the difference with it is that you see this thing here, that is actually a optical glass plate. and it has a very, very small curve in it. And what it allows you to do, that you can have a secondary and primary mirror that are both spherical. So they're easy to fabricate, no hyperbolic mirrors or anything like that. And the optical errors that cause can be cancelled out with this corrector plate, as it's called. And you notice the secondary mirror is actually installed, mounted in a hole in the central part of the corrector. So mechanically fairly simple. One slightly odd thing with these telescopes is that generally with the other types of telescope, you have a focuser on the back here that moves the eyepiece or your camera in and out. The way these work is that they focus by moving the main mirror. And you can get away with that with a Schmitt Casagrain because the optical design is quite forgiving. It would never work with a Ritchie Creation telescope I showed before because the distance between the two mirrors is quite critical. So yeah, but they decide by just having some threaded arrangement that focus by moving the main mirror, and the commercial ones all work like that. The Meade and Celestron are the main ones. Are there any others, Steve? Yeah. Yeah. Okay. So another design is called a Maksutov Casagrain. So this is a bit harder to fabricate, but amateurs have built these. And the idea is a little bit similar to the Schmitt Casagrain, that you have an optical corrector in the front of the tube. And you see this is quite a thick corrector plate, and sometimes called a meniscus lens. And in this case, the secondary mirror, it turns out the way this design works is that the secondary mirror is just aluminium coating on the inside of the secondary, so you don't need an actual housing or anything mechanical for the secondary mirror, because it turns out that the shape of the backside of the corrector plate is exactly what you need for the secondary mirror. So it's quite a clever design. In fact, we have a 12-inch one in the storeroom over the back there, which has been looking for a home for many years. Right, so that's kind of covers the main types of telescopes that amateurs come across. There are some other ones. There's one that's coming popular for imaging these days is there used to be a popular telescope for planetary imaging, a reflector called a dual curcum, which was really good right in the centre of the field, but when you got away from the centre, it had quite bad aberrations, so it was no use really for imaging. But nowadays they sell what they call corrected dual curcums, which have an optical corrector that fixes that issue, so you get a really large corrected field for use with a camera. And I don't know if there's any around in New Zealand, but they are quite popular with larger telescopes overseas. So we go on to the next topic, which is actually, before we do this, before we move on, are there any questions about telescopes or any telescopes you're interested in, like to tell us about, or designs?
Yeah, I've got a question, Bill. I've got a Meade SCT, and it has got the adjustment on the back of it to move the mirror backwards and forwards and a mirror lock.
Yeah.
But it's also got a focuser that adjusts the eyepiece in and out.
Oh, so it does both.
Yeah, that's right. So I guess you're suggesting that if I wanted to go for the best possible picture, if I could work out what that mirror distance was and set it to there before I adjusted it backwards and forwards on my other focus.
I think that's right, actually, Grant. With your one, you have they've got a Schmitt Casagrain, another type of Schmitt Casagrain that's got slightly different optics to correct for coma as well. better than the standard Schmitt Casagrains. It's called an Meade ACF telescope. And you definitely would have the main mirror locked, Grant?
Well, in the bigger size, that's a 16-inch one up there. So the primary mirror is fairly heavy.
Yes.
And so in our experience, you know, you're better off to lock the primary mirror and just use an electronic focuser on the back. So the one up there has got a temperature compensating focuser because the telescope extends and contracts with temperature.
Okay.
So the focus would want to be moving and you'd be losing your focus all the time.
Yes.
So basically the trick is that you spend extra dough, like another couple of grand, and get a temperature compensating focuser that will measure the temperature of the tube, and then you calibrate it so that the focuser takes that out of the equation, so you can maintain sharp focus as the temperature changes through the night.
Oh, I see.
So, but the one up there too has also got a slightly different shaped corrector plate. So what Bill was alluding to there was that instead of going with the one that actually mimics a Cassegrain, which is what this normal Schmitt Casagrain is, the one up there, the corrector plate's been adjusted so it performs closer to a Ritchie-Cratian, which is so it's a cheap way of getting something closer to a Ritchie-Cratian. It's not without sort of some of the dramas of trying to collimate a Ritchie-Cratian. It's much simpler to work with. So, but the penalty you pay is that you've got your light coming through a corrector plate, which it's dispersive, so that the red and the blue light, you know, wavelengths get separated. So it's not simply. So as soon as you put a refracting element into the thing, like the Schmitt Casagrains and the ones like ours, you do get that chromatic aberration.
I see.
Yeah, that's what we were talking about earlier at the beginning with the issues with refractors, because unless you get a really expensive lens, they suffer from chromatic aberration because of the dispersion of light through the glass. So the other thing about the Schmitt Casagrains is that if you use them for visual, they're fine, but the standard ones with the moving mirror focuser, they can be really annoying for photographers because the Meade ones especially, I think, are known to have a mirror that can actually flop around in different parts of the sky. So yeah, so that's really annoying for astrophotographers because it can mess up the collimation a little bit. Probably not an issue visually, but it definitely is for photography. Okay, so we've got our telescope sorted, but unfortunately you can't really use it for anything at this point. You've got to either put a camera on it or use an eyepiece for visual observation. And generally the eyepiece will be a refractive element of some kind. So the really simple one at the top here, the diagram looks quite complicated because it's showing a whole lot of rays coming from different angles. But the idea is that you have your objective lens at the front, and then you notice the eyepiece in the top one, so-called Galilean scheme. You've got a lens which is concave, and this is a negative lens. But the reason that they like this, because telescopes were originally used for terrestrial purposes, and this gives you a correct image. In other words, the image is the right way up, you know, just as you'd see with your eyes. But the problem with that kind of eyepiece is that it also gives you a very narrow field of view, so it's a bit like looking through a drain pipe or something. So you possibly heard of Johannes Kepler, famous for his 3 laws of planetary motion. He came up with an improved design for the eyepiece using a convex lens, an ordinary magnifying eyepiece as we would call it, and the disadvantage of it is it actually flips the image, but when you're looking at the sky it doesn't really mean anything, so who cares what way up it is when you're looking at something in the sky. So pretty much all astronomical telescopes use some variation of the Keplerian scheme for visual observing. Okay, so eyepieces. For historical reasons, the barrel size of the eyepiece is always imperial measurements. So there used to be telescopes that had 0.965 inch. Very rare these days. I don't know if people have ever come across Questa. They made a little Maksutov telescope that was really popular as a table-top telescope, really well machined, and they came with a screw-in 0.565 inch telescope, really expensive but superb optical quality. I think there are a few around in New Zealand. Have you come across any, Steve?
Yeah, a few older telescopes.
Yeah, they're kind of a collector's piece, but yeah, pretty much you have difficulty sourcing one of them probably, one of those type of eyepieces. But a lot of the old department store type scopes used to come with those, but I wouldn't recommend them. They're not quite a Questa.
I used to have a 114 mil with a 0.965 eyepieces.
Right, okay.
Various designs, Hartskins, H and Canada
Right.
eyepieces.
So the two common sizes these days are the 1 1/4. Oops, I keep pressing the wrong button. Sorry about that. Oh. We talked about APOs and all that. Oops, okay. So generally you'll have either 1 1/4 inch eyepieces or 2 inch eyepieces. And typically it's quite common for a telescope to come with a 2 inch focuser, but you can still use the 1 1/4 inch eyepieces with an adapter, which obviously just a sleeve that fits inside the 2 inch focuser, and then you can put the 1 1/4 inch inside that. So there's a little trick here. So if you were generally wanting to do planetary viewing, which one would you probably be using? You want high magnification for planets, so...
The 1 1/4.
Yeah, why is that?
Because there's more eyepieces.
Well, the focal length of those is generally shorter.
Yeah.
And the shorter the focal length, the higher the magnification. And for observing planets, they're bright, so you can afford to magnify them a lot without dimming them, and that way you get to see more detail. Whereas if you're doing deep sky imaging, you're probably more likely to be using a 2 inch eyepiece at a lower magnification. So I think one of our outreach volunteers always asks people which one will give you the more magnification. He shows them the big 2 inch barrel eyepiece and the small 1 1/4, and most people think it's the 2 inch one that will be the one to get the high magnification, but it's actually the other way around. So eyepieces, as well as a barrel diameter, they have a focal length, and the focal length, the shorter the focal length, there's a formula. You basically divide the focal length of the telescope by the focal length of the eyepiece, and that's your magnification. So that's how that works. But the other thing, a characteristic an eyepiece has, is what's called apparent field of view. And what that does, for a given magnification, you can get an eyepiece that gives you quite a narrow view, and it's like sort of looking for a drain pipe, as I was talking before, like the Galilean type eyepieces. Or you can get ones that the same magnification but allow you to see a really big field. There's even nowadays you can get ones that show you a field of 120 degrees, if you imagine what that's like looking from your eyes, versus like that if you had to look through a pipe. So the magnification's the same, but you've got a much narrower field of view, or a wide field of view. As you can imagine, the higher the more the field of view, generally they're more expensive, because to do that they have to use more complex optical design. Okay, so here's an example here of some really wide field eyepieces. Do you still sell them from Astrons? They had a brand called Sky Rover that was similar design to these, that had a 82-degree field of view. I'm not sure if they're still available. Yeah. Yeah, I actually bought one myself because it's really just lets you see a much bigger field at a given magnification.
But 230.
The GSO Super View, that's probably, I think, 67 degrees, something like that. So that's sort of an intermediate one. These ones come from the company called TeleView. You can see they've got a really complex design with a lot of complicated looking glass elements, and they have to do that to be able to give you that wide field of view with sharp image way out to the edge of the field. And the one below is the same company, but they branded, instead of Nagler, they call it Ethos. And there are other brands like the Sky Rover one I mentioned, and so on. Yep.
With the extra lenses, I gather the type of glass they're using almost has zero internal reflection of the light.
Right, yeah, actually that's a good question. Right back at the beginning we showed that diagram where a ray of light was going through a refractive surface, and a little bit of it was reflecting. Now imagine that's happening on all the surfaces in here. That would be really terrible. You'd be getting a whole lot of light bouncing around inside the eyepiece, and what the effect would be that it would lower the contrast of the image because it would be lighting up, all smearing out the background. So how they deal with that is they put special anti-reflective coating on the lenses, and it basically suppresses that reflection you get. Like if you just look in a window pane, you can see the reflection in it if you look at a certain angle especially, whereas with an optical lens that's got a proper anti-reflective coating on it, it'll much reduce that effect. But it obviously adds to the cost because all of the surfaces have got to have the anti-reflective coating applied to them. Yeah. In fact, if you ever look at binoculars, you could see the really cheap ones had a sort of an orangey coating on them. So definitely stay away from those because they're not very good. The ones that have got a good anti-reflective coating on them, they'll tend to have a greenish, very pale greenish tinge.
My guide scope is Sky Rover. That also has a 23mm rect, which I place into it, which is 1 1/4. And that is actually one of those.
Oh, okay. An 82-degree field eyepiece. Yeah. Okay.
It's 23mm.
Okay.
Wide field.
Yep.
Because seeing wide field 7 degrees, something like that.
Okay. Oh, okay. That's the whole field. That's the true. There's a little bit of confusion here. What we're talking about here is apparent field. So that's not the true field on the sky. So when you combine this eyepiece in with a telescope, the true field will be much smaller because the telescope is only looking at quite a small patch of sky. But this apparent field is what it looks like to your eye. So in other words, your eye can move around 82 degrees from side to side, and you can see that. But it can still be quite a small patch on the sky because the telescope is only, the longer the focal length of the telescope, the less the patch of sky that you'll be able to see. So binoculars typically give about, or finder scopes, typically about 6 degrees of what's called the true field on the sky. Oh, yeah. Oh, sorry, yeah.
How much do those ones cost compared to more simple ones?
I think the one, I can't remember, the typically 3, 4, like I know that these TeleView ones, which was sort of the premium kind of brand, I suppose you could call it. You pay for one of those, if you had an 8-inch Dobsonian, the eyepiece would actually cost more than the telescope. So,
I mean, a set through our ones was that, so say just around 15mm eyepiece, 50-60mm eyepiece, a Plosser would cost you around $40, a wide angle would cost you around $50, which is 60-65 degrees. A 70-degree eyepiece might cost you around $100, $75, $100 up there, or a flat field version, around the $100 mark. When you jump up to the 82-degree ones, it really jumps up to about $300. And then if you go into the the extra wide angles, so you have 100-degree apparent field of views, you jump up to about $600, $600.
yeah, and the teleview ones would be even more expensive.
And the teleview ones, you get $800 US plus GST. So yeah, $600. So, but yeah.
They do give amazing views. I don't know, we used to have a guy in the club called Dave Morehouse, and he built a binocular telescope with 16-inch mirrors, and it often used to go to the star parties, and that had absolutely stunning views, and it used Nagler Type 2 eyepieces for 82-degree field. And from a dark sky sight, absolutely amazing views, especially because you could look with your two eyes. The way it worked is you actually were looking down like this, and you were between the two telescopes, so basically the two tubes were looking at the sky behind your head. It was the way it worked.
They were called the Records.
Somebody bought it. I'm not sure who's got it now. Yeah.
So Bill, all of those lenses there, are they all inside one eyepiece?
Yes, yeah, they're all in. Yeah, I mean, if you ever took a camera lens apart, you'll find the same sort of thing, especially if it's a zoom lens. To make it work over a wide range of focal lengths, they have to have a lot of optical elements in there. If it gives good images, it's going to be expensive because of the amount of work to manufacture all that.
Those optics I was talking about range, where the simple Plosser was 4 elements, two pairs of lenses, up to the big fancy ones were 9 optical elements in groups through the eyepiece. So it's only going to 9 lenses that all have to craft together and all coated to work together and stuff.
Yeah, and some of these will be very exotic glass types as well. And what has this one got? It's got 1, 2, 3 groups. You've got 3, 1 plus 5 in there. So there's 9 elements. Okay, another type of lens that is really often used by amateurs is a lens called a barlow lens. So this is actually a negative lens, a bit like the eyepiece used with the Galilean type telescope, but what you use this for is not on its own. It's used in combination with a normal eyepiece, and typically the barlow will be, sometimes they will be designed as a focal length doubler or maybe a tripler. So what you do is you buy a barlow, and if you've got a selection of eyepieces, it basically doubles the different magnifications that you've got available to you. If you've got a 2 times barlow and you had a 10mm lens and a 30mm lens, the barlow means that you get a 5mm and a 15 as well. So not really, but that's the effect of it. So basically it extends the range of magnification that you can get with the set of eyepieces that you have. And the diagram sort of shows it. So here's the objective lens focusing the light, and the barlow sort of defocuses it and brings it to a focal point way back here. So it looks to your eye as though it was coming from here. So in other words, it sort of increases the apparent focal length of the telescope, and so I'm not sure that the geometry is quite right in this diagram, but that's basically how it works. So you can also, a lot of people that do planetary photography will use just a barlow with a camera, because with a planet, they're very small on the sky, and you put a camera on, you get a really disappointing image with a, say, even a, I don't know, a 1 or 2 metre telescope. So you use the barlow in combination with a camera to blow out the focal length, and so you're effectively magnifying the size of the planet that on the film plane or the image sensor. So the barlow lens is used both for visual and for photographic use. And we have another kind of lens which is the opposite of a barlow, and that's called a focal reducer. So instead of increasing the focal length, you want to reduce it. And for example, Schmitt Casagrain, I think if you were here for the earlier talk, the guy was talking about his 2 metre focal length in the 8-inch Schmitt Casagrain he bought, and he found that was quite difficult because long focal length, more magnification effectively means that your tracking and everything has got to be just that much more accurate. It's a lot more sensitive if you're doing photography. So, well, that's one of the reasons you use a focal reducer to pull that back. And it also means that you don't have to expose for long because the light is concentrated into a smaller image circle. So you can expose your image much faster. So they're not really, I don't know anyone who uses a focal reducer visually, but they're definitely used for photography. Is anyone here, you have one or use one?
I've tried one for getting a better image of the moon through my Schmitt Casagrain.
Oh, right.
Rather than
So the moon was too big to get on the on your camera sensor.
no, visually.
Oh, right, okay, yeah, okay. Right, so you weren't doing it for photographic reasons. But I know a number of people use them.
Yes, I still use one for astrophotography.
Oh, you do, okay, yeah. Okay. So another kind of thing, and again, this is really used for photography, is what's normally called a field flattener. And you think, well, what the heck that's about? Well, for example, this is really exaggerated, simple case showing a lens, and you've got a focal point in the middle here, but you notice that the focal point, when you go out to the side, isn't on that flat plane. So the focal plane is actually not a plane at all, but a spherical surface. So this is highly exaggerated. A real telescope wouldn't have a focal plane as curved as that. But it does have a notable effect that when you get away from the middle of your image, the stars will start to get blurry and out of focus. And it's basically field curvature that's causing that. You've got a nailed focus in the middle, but on either side of focus, as you get further away, the focus gets worse. So how bad this is depends on the design of the telescope. Ritchie creation obviously is pretty good, but it still does have a bit of curvature. The one I mentioned, the corrected dual curcum, corrects further out than the standard RC or Ritchie creation. So basically, depending on what sort of telescope you're using, you may have to use a field flattener, so that because your camera sensor is flat, it'd be different if you had a curved sensor, and such things do exist. I think, has anyone heard of a Schmitt camera? It was a type of telescope. George has heard of it. Yeah. Basically, the way it worked is that they didn't care about the curved focal plane because they actually had a curved film. So they'd actually load it up with a curved film, do their exposure. I've never heard...
Your eyes are curved too, aren't they?
That's right, so you don't even need this for visual observing because your eyes will just adapt as you're looking around the frame, you will be automatically adjusting.
Is that why Richie Crichton's not so good visually, because they produce a flat image?
No,
Shouldn't be.
The main reason I think is because the secondary mirror in an RC is quite large compared to much larger than other optical systems, and so just you drop contrast because
especially for planets that's right. There's a big central obstruction, so that's the reason. I don't know if you've ever tried it, but you might wonder, well, we have these mirrors in the middle and we have holes in the main mirror. You have a secondary in the middle of the tube. So when you look through the eyepiece, you can't actually see the secondary. But in actual fact, that's because at night, your eye pupil, when you're dark adapted, is open quite wide, and your eye focuses what is actually a donut of light hitting your lens, but it gets focused to a point on your retina, so you can't actually see what's called the shadow of the secondary mirror. But if you use Newtonian daylight, your pupil shrinks right down, so the donut might actually not all get in your pupil during the day, so you can actually see the shadow of the secondary. So Newtonian telescope, not quite so good for using during the day.
When I use eyepiece protection on my 6.8 digital camera DSLR, I end up getting curved images. It's good in the centre, but rainbow up the edge.
Okay.
That's why I need something like that
Right.
to flatten the...
Well, that may, if it's rainbow though, that would be chromatic aberration. What this is trying to fix isn't the colour fringing, it's just stuff being out of focus, because as you see, the focal point depends on where you are, and so it ends up being a curve. No telescope would really be that bad, except where it's done deliberately, like in a Schmitt camera, and they have a curved film holder to... of course, I have heard that you can get curved digital sensors as well these days, but I don't know if anyone has ever...
Just my
Possibly.
is fine. There's no problems with the field of view in that way. When I'm taking photographs through the actual telescope itself without the eyepiece projection, but with with an eyepiece in it, it does cause that problem of rainbow type of trailing, and as well as curved stars.
Well, yeah, you can have both problems. All of these spherical aberration, coma, chromatic aberration, you can combine them all and get a really, really bad image.
That's for an eyepiece, though, mind you.
Okay. One other thing that we use are filters, and for example, if you've ever looked at I'm sure most of you have looked at the moon through a telescope, and it's really, really bright, and it actually dazzling your eyes. So what's quite common is to use a neutral density filter. So it's just a bit of optical glass that blocks a certain percentage of the light out, and will screw onto the eyepiece barrel usually. And and there are other ones that are used visually. There's these ones here called an O3 filter as an example of what's called a narrowband filter. The neutral density one blocks all the different colours about the same amount, whereas the O3 filter is looking at a particular spectral line of the oxygen atom. And why you would want to look through that is because it blocks out a lot of the background light, but it allows the light that planetary nebula emit. So it will actually, if you're looking at planetary nebula especially, it really shows them up in more contrast. And then you have a thing called a UHC filter, block light from artificial sources. This is interesting because sodium vapor lamps, you know, that sort of yellowy colour, it was possible to have a filter that would block that light out, so a lot of that sodium light is getting reflected from the sky as sky glow. And you could block it by using a filter with really good for photography. Trouble is they're replacing them with LEDs, and LEDs are broadband, so you can't actually filter out the LEDs. So they're great for power efficiency, and you notice, I don't know if you've seen where they've put them in on the motorways, but the shields on the LED lights, they are very good cut-off. They just shine down, not into your eyes as you're approaching them. You don't get them blinding into your eyes until you're really right up to them. And so that's the idea, that they not casting light where it's not needed. But the problem is because it's broadband, all colours, and especially strong in the blue, which is actually bad for people at night and wildlife and what have you. So they do have a downside. So this kind of filters aren't suitable for looking at the sun, of course. For that you need a special blocking filter. The Society actually owns some that will fit over an 8-inch telescope. So that's a full aperture blocking filter, so you don't put it on the eyepiece. If you ever have a telescope that comes with a solar filter that you put on the eyepiece, don't ever be tempted to try it. It's really dangerous, because what will happen is if the sun's focused down at the eyepiece end, it's going to get really, really hot. That filter might work, but it could easily shatter from the heat, and you're risking your eyesight. So if you're ever doing solar observing, use a proper solar telescope. One of these filters that covers the objective, so that it's not going to be having concentrated sunlight at that point.
Or use a sun projection screen, which is basically...
Where you project it onto something, so you're not looking at it directly, yeah. That's another safe way to do it. Okay, just some definitions to confuse everybody to finish with. I probably should have put these at the beginning. Right. So you've got this big letter big D. When you see that, it's referring to the aperture size of the primary lens. And then what this little equation is saying, that the sine of some angle is equal to 1.22 times lambda, which is the wavelength or the colour of light, divided by the aperture. So as the aperture gets bigger, this number gets smaller. And what that means is that the bigger mirror can resolve smaller detail. And so that's why you want a big, not only because you capture more light, but in theory, all else being equal, you'll get more detail with a bigger mirror as well. So you see the term F, big F, the focal ratio. As I mentioned before, that's the ratio of the focal length of the telescope divided by the diameter of the objective. And small ft, that's the focal length of the telescope. Fe is the focal length of the eyepiece. And then you've got these other things, apparent field of view, if you ever see that, true field of view. And so the true field of view is the actual amount of sky you see given that telescope and eyepiece combination. We have another thing called exit pupil size. So this is actually quite easy to see in a pair of binoculars. If you hold the binoculars away from yourself and look at the eyepiece and you have a bright scene there, you will actually see a spot of light on the eyepiece of the binoculars. Well, that round piece there is the exit pupil, and it basically means that you want that to be quite large so that but not so large that it doesn't all go into your eye's pupil. I hope I'm explaining that right. If the exit pupil is too big, and so let's say as an older person your eye might open up and dark adapted to 5 millimetres. So if you had a lens with a telescope combo that had a exit pupil of 7 millimetres, then you'd actually be not seeing all the light. not necessarily a problem, but that's just something to be aware of. And the eye relief is quite important. That's where you have to position your eye to be able to see the entire exit pupil. And basically that matters for people who wear eyeglasses. If you don't need eyeglasses to look for a telescope, you can get your eye close to the eyepiece. So the eye relief doesn't matter to you because you can get really close. But if the eyepiece had a short eye relief, you're not going to be able to use it wearing glasses. And generally you'll only need to use glasses if you suffer from astigmatism. If you're just short-sighted or long-sighted, you don't need them because you can just refocus the telescope to correct for either short-sightedness or long-sightedness. Another term is the M, which is just the magnification. And some formulas. Focal length of the telescope is the diameter of the mirror by the focal ratio. Give some examples here. I should actually put this document up on the website so you can refer to it. And here's how you calculate the magnification, is the number 2 item there. So you take the focal length of the telescope, divide by the focal length of the eyepiece. So if you've got a 200mm f6 Dobsonian, which is the sort that the Society rents out, so if you use that with a 25mm eyepiece, magnification would be 48 times. So you can just use that formula to work out the magnification for any telescope and eyepiece combination. I'll skip over that, but I will put this up on the website. So that's how you can relate the magnification and the apparent field of view and the true field of view. So we'll skip that because we've run a bit over time. So we'll just finish with any questions.
If you can't remember all these formula, there's a great website called astronomy.tools, which lets you put your telescope details in. You don't remember them, you choose your telescope off the list, put either eyepiece or your camera details in it, and you choose an object, so like the Orion Nebula, will show you the field of view, how the object fits into that particular eyepiece's field of view. It's a good way of just looking at your telescope and trying different eyepieces to see which eyepiece is going to suit me best for the sort of viewing I want to do.
Yeah, I think Stellarium has got a plugin that does that as well.
Yeah, a lot of the nice guys.
If you ever use the Stellarium Planetarium program, there's an eyepiece plugin for that, and you tell it what your telescope is, the focal length and the aperture. You tell it the focal length and the apparent field of the eyepiece you're using, and it'll actually draw on the screen a circle that will show you what you will actually see on the sky with that combo. So that's quite a handy little feature as well. Any other? Oh yeah, you got a question here.
What exactly is coma and when do you need a coma corrector?
Okay, well, I didn't want to go too much into optical aberrations because it gets down into the weeds pretty quickly. What that is it's an aberration that Newtonians especially are notorious for, especially if they are what is called a fast telescope with a really short F ratio, like especially say an F4 telescope. You'll notice away from the centre the stars get smeared out with little tails, and the same root of the word comet. So it's an aberration because instead of bringing the image of the star to a point, it actually starts smearing it out. And you can get a coma corrector to fix that. And generally with an F6, visually you wouldn't really worry about it, but you definitely notice it visually with an F4 telescope, some of the ones with really big mirrors, because you don't want the eyepiece way the heck up here. You want a shorter focal length, but they will suffer from coma. And in fact, camera lenses suffer from this as well. Jonathan's still here, he would...
They definitely do.
Yeah, if you don't get a good quality camera lens, you'll notice in the corner for you don't notice it so much for terrestrial viewing because you don't really care that the edge of your image and all the top corners are a little bit blurred from coma, but you'll definitely notice it using a camera lens for astrophotography, because you can see the stars will, and the corners especially, will be smeared. So you would have seen this effect if you don't have a really good quality lens.
I've got a 6-inch telescope, which is f4 from Andrew.
Okay.
That does actually, with the eyepiece, does show that covered sort of thing when you're doing vision.
When you go away from the centre of the field, yeah. And you can get a lens that basically corrects that error. It's one of the optical aberrations.
Like, it's called, which Andrew told me, you can get field flatteners as well, eyepieces.
Yeah.
And $100 each.
Yeah, a field flattener you don't usually need for visual use, it's more for photography.
Yeah.
But definitely a coma corrector, if you've got a fast Newtonian, then a coma corrector would be really useful. In fact, I think the big binocular scopes, they did have a coma corrector built into it.
They can do so, and it was just like any optical system that's not perfect. You put a corrector lens on, a pair of glasses or a corrector lens in, you correct out the aberrations. For a Schmitt Casagrain telescope, it'd be the corrector lens in the front. For a coma, because even SCTs have coma in them to an extent.
Yeah, that's less than Newtonian.
So you put a corrector lens on, correct out. That Hubble Space Telescope in a top, you put a corrector lens to just work out the file.
Okay.
Got a couple of questions from the internet.
Okay.
We've got. I'm looking for a budget-friendly, dedicated astro camera. The more expensive ones are cooled. Can you please explain why cooled cameras are better for astrophotography?
Okay, so any digital camera will have sources of noise, and for example, for astrophotography, you're usually taking a long exposure because you want to gather as much light as possible to be able to see faint objects. And all of the different kinds of digital cameras, there's CMOS ones, CCD ones, you take a long exposure, they're not only recording light, but they're also recording what's called thermal noise. And so if it's at room temperature, the thermal noise will be at a certain level. And if you keep exposing and exposing, eventually the thermal noise will swamp the picture. So the way around that is you basically have a built-in refrigerator in the camera that cools it to maybe minus 20 degrees centigrade. It means you can take much longer exposures before the thermal noise becomes a problem. A normal digital camera used terrestrially, you'd never notice this because the exposures might be a thousandth of a second, a hundredth of a second. The thermal noise that's built up over that time is negligible.
I thought standard digital cameras also filter out certain light that you don't want filtered out.
Oh,
That's a different thing to noise. They will generally filter out infrared light.
Yeah. So, and you can actually get a cheap, say, digital camera, and you can alter it so that filter is turned off. The trouble is you can't turn it back on again.
Well, the filter actually has to be physically removed.
Yeah.
And so you would void your warranty, I would imagine. But there are people who do this specifically for astrophotography, because taking the infrared filter off means that more light gets through. So and also the sensor is then picking up a lot more light at the red end. And if you see pictures of things like the Orion Nebula, you'll notice there's a lot of dark red, deep red colours in there. So basically you'll pick up more of that colour by removing the infrared filter, because it's not perfect. It doesn't just block infrared, it blocks some of the deeper red as well.
Yeah, but you can get specialist cameras where they've actually set it up for astrophotography.
Yeah, that's right. But yeah, that's a kind of a different issue to is the question are happy with the answer about noise.
The astronomy, the cooled astronomy camera is also a tweaked for astro imaging, so for the extra features, like anti-blooming stuff and anti-dewing technologies and things to suit that.
Yeah, if you ever try astrophotography with a normal camera and you stick it outside on a nice winter night, I think you're going to take a series of long exposure photos, and then after a quarter of an hour you're sort of looking at the images, inspecting the images, and suddenly they've just turned to complete blur, and you look at the front of your lens and it's covered in dew. So there are various ways you can get dew heaters and dew shields, and I think some people even use hand warmers. They have a powder in them, and you shake them up and they have a chemical reaction that generates heat. You wrap that around your lens to keep the dew off. They use all sorts of tricks like that.
Going back to the whole noise thing and why using a cooled camera, it's possible to calibrate out that thermal noise from your images, but in order to calibrate out that thermal noise, the calibration frames have to be taken at the same temperature as what your light frames were taken at. And so if you've got a cooled camera, you can control what your calibration frames are and your light frames are.
Right, so every frame is taken at the same temperature, whereas if you just, over the course of the night, the temperature will be, just the ambient temperature is going to be changing all the time. That's right.
And if you're using a DSLR and you try and calibrate out the thermal noise, the temperature change is just going to make it more difficult. So it's much better to have that cooled camera with your calibration.
Unfortunately, it means a camera like that is dedicated for astrophotography. You're not going to be able to use it for terrestrial use. Like a DSLR is a multi-purpose camera, and you can still get pretty good astro pictures with a DSLR. I'm sure you've seen them, or one of the newer mirrorless cameras. Did you have one more internet question there, Steve?
Yeah, there's one. There's a couple, but I'll ask you this one. Can you explain the resolving power of a telescope?
Okay, I haven't got the diagram, but if you were to focus your telescope on a single star and really magnify the image in, you see that it's not actually a point. It's what's called a diffraction pattern, and you'll see that if you draw it on a plot, you'd see a big, strong central peak at the centre of the image of the star, but surrounding the star there will be these rings, and the rings are lower and lower magnitude as you get further away from the point where the star was focused. That isn't an optical flaw, it's actually the way light works. And what a guy called Airy worked out, that if you have two star images that are really close together, like a double star, he came up with a formula for how much aperture you need in your primary mirror or your lens to be able to tell that there's actually two stars and not one. And so it works out that the separation between those two central parts of the image of the star depends on the size of the mirror. So essentially, the bigger mirror, the more separation you get between them, and the easier it is to resolve the two stars rather than just seeing it as one star. And if you have a small aperture that shows one star, it doesn't matter how much you magnify it, you won't be able to separate them because the two, they're called Airy discs, are overlapped.
What do you measure that resolving in?
It's measured in generally arc seconds, usually. Yeah. So in other words, if you do visual observing, you might be able to see the two stars that are maybe 5 arc seconds apart. That's quite difficult. One arc second becomes really difficult because the actual sky seeing isn't very rarely that good at sea level. So the turbulence in the air is shifting things around, so the two images of the stars are not steady, they're wobbling around as well. So you end up, you can't just have a bigger and bigger mirror because the atmosphere will start blurring what you're seeing. And that's why the big professional scopes are up on mountains, like all the Atacama Desert in Chile, where they're really high, maybe 12,000 feet above sea level, and it's really dry, and they're above a lot of the atmosphere. So it means that they can actually use their big mirrors to do that, whatever resolving they need. And that's why space telescopes as well, because then you take the atmosphere out of the equation completely.
Final question, here's a good one. Which is better, a refractor or a reflector?
Oh, well, I don't want to go into that argument.
Yes is the answer. The answer is just yes.
That depends.
It depends, yeah. There is no perfect optical system. It depends on what sort of use you're doing, and there is a compromise to everything. You win one way and you lose another feature. And this is why some people end up with multiple telescopes. Even look at Joe Nick's talk earlier on, he has 3 different scopes. One for doing long focal length, big aperture, one very short focal length for wide field, and a refractor in the middle.
Yeah.
So he's got 3 different scopes for 3 different purposes.
If you went back to the 17th century, you'd say definitely, or even the 18th century, you'd say definitely a refractor. And that was because Newton had invented the Newtonian reflector, but the problem was the quality wasn't very good. The mirrors were just made of highly polished metal, and so it wasn't until they found that they could use a glass substrate which could be polished really well and overlaid with a silver or aluminium reflective coating that the reflectors came into their own. And then when you get to bigger and bigger telescopes, the reflector always wins just because of cost and the fact that building the largest refractor ever built, I think, had about a 40-inch or just over a metre diameter. And that's because you have to hold this great big assembly up in the air. So you've got mechanical issues with flex and all the rest of it. Whereas a big mirror, you can have nicely mechanically supported. So when you get to really big pro telescopes, you definitely reflectors win. But for amateur use, it depends on what you're doing.
Some of you maybe here, we had, it was late last year, we had just outside after a meeting, we had the 4-inch 100mm binocular telescopes, really high-end refractor, lovely optics, next door to a 8-inch Dobsonian, Newtonian telescope. And we looked at the same optics with people and said, which is the best? And the result was, it depends. It depends on the object looking at. Some of the open clusters were better in the smaller aperture refractor because it higher end optics inside and had a nice wide field of view. You could see a big open cluster look beautiful, the whole region around it. Looking at a globular cluster, the Dobsonian one easily, because they had 4 times the aperture and their cluster actually resolved out. Whereas in the small aperture it was still a fuzzy blob, a bit blobbish basically. So it just depended on what you're looking at and what sort of viewing you're doing.
Okay.
If in doubt, buy 3 telescopes.
Okay, we better finish there. We've gone way over time. Yeah, Andrew will always sell you telescopes, don't worry. Okay, well, thanks for coming along, everyone.
Thank you.